Hello Math 4411 students, let's begin lesson 10, this time for real. Let's go to section 4, factor groups, and let's define it. And we're going to use two different approaches. One is about kernel, but this approach is a little bit easier to understand, but it's not general enough. Now the second approach is using the normal subgroups. That's general and that applies to all factor groups, but we have some steep learning curve, especially in the beginning. Later on, they will turn out to the same. Both approaches will be equivalent, and that's what we're going to establish in section 5 through fundamental homomorphism theorem. Okay, all right. The first approach is using kernels. Here's a reminder. Let phi be a homomorphism from a group G to another group G prime. And the kernel of this homomorphism is defined like this: the preimage of the trivial subgroup of the target subgroup G prime. In other words, it's set of all elements of G, the domain group, whose function value is E prime, the identity of the target group G prime. It's a preimage of a subgroup, so it's a subgroup of G. That much is certain. And furthermore, we can prove that the homomorphism is one-to-one if and only if the kernel is just trivial, just E alone and nothing else. Now, most importantly, we can prove that, there's a typo. Okay, now it's corrected. Most importantly, we can prove that the left coset and the right coset are always the same as far as the kernels are concerned. In other words, the kernels are normal subgroups. Now, how did we prove this? In the proof, we actually proved something stronger. We proved that left coset is the same as this, the pre-image of phi of a, the function value, and also this set is the same as the right coset as well. And this is a key. Please remember this expression. By the way, this expression is a shorthand of this. Remember, if you have a singleton, just one element set, then it is customary to just drop this brace out of simplicity and write like this. Okay, so much for the review. And remember this red thingy here. Let's go to factor group. Let phi be a homomorphism from a group G to another group G prime. Let K be its kernel and let phi of G be its image. So the kernel K is a subgroup of G, the domain group, and the image phi of G is a subgroup of the target group G prime. Okay, so far so good. Now define a subset G slash K or G over K of a power set of G. In other words, every element of this is a subset of G. So this thing is a subset of power set, and we define like this. G slash K is defined as the pre-image of an element of the image set. Now, Y is an element of an image, so Y is a certain function value. So if you rewrite like this, Y is phi of x, then we can rewrite like this. You see, Y is phi of x, so phi of x belongs to G of G. And furthermore, what do you mean phi of x belongs to phi of G? Everything came from G, so you can reduce that into just x belongs to G, like this. And then one more observation. Preimage of phi of x. Haven't you seen this before? Yes, that's a coset. The coset of the kernel. And then the coset of the right kernel as well, as a matter of fact. The left coset and right coset are the same. So because they're the same, I'm not going to use the right coset anymore. I'll just use left coset. Remember this? We went through that already. And the proof was rather complicated. We had to prove both inclusions. But that's something we already did, so I'm not going to redo that. Just remember this expression, the preimage of the function value. Okay, we got the definition now. Now let us define an algebraic operation in this set, G over K, and we're going to define like this. Arbitrary element here is of this form, preimage of some y. So another preimage of some other y, so y1 and y2, and we define it as preimage of y1 times y2. Now this operation, y1 times y2, is a group operation in G prime. Remember, phi of G is a subgroup of G prime, so phi of G follows the algebraic operation of G prime. And G prime is a larger one, and this is a group operation in G prime. So this definition of this algebraic operation was induced from the group operation in G prime. And then with this set and with this group operation, we must prove that the G over K is a group, and not only that, it is isomorphic to phi of G. We're going to call this group the factor group of G modulo K, or over K. Basically, we have to prove these two. G over K is a group under the binary operation defined this way, and that's associative, has an identity, and each element has an inverse. You have to prove those. Can you do that? I'm going to leave that as an exercise for you. Associativity, well, we have to consider y1, y2, and y3 instead of appropriate parentheses. And then you'll have to use the associativity in G prime because the operation was induced from that of G prime. Same for the identity. Identity must be induced from that of G prime, so E prime must be involved somewhere, and same goes to inverse. Good luck about that. And then we have to prove that that group is isomorphic, which means we have to prove there's an isomorphism from G over K to phi of G, or vice versa, because isomorphism is bijection, so either way. Further detail is left to the students. Let me give you just one more hint. I would prefer to have vice versa, and we define like this. F is a map from the image subgroup phi of G to this factor group G over K defined like this. What's the arbitrary element of phi of G? Well, no, not that. Arbitrary element is y, so y is defined as phi of y like this. After all, that's the definition. That's how we define, yes? And that's a natural map from phi of G to G over K. And you have to prove that this map is number 1, 1-to-1, number 2, on-to, number 3, homomorphism, so that this is an isomorphism. 1-to-1 may need a bit of an effort, but it's not going to be too bad. On-to is trivial. You don't need any work because it's defined this way. Everything is defined this way. So it's clearly on-to is trivial. And as for homomorphism, well, algebraic operation is defined like this. So you have to use that and rewrite in place of f in terms of f. And the preimage should be rewritten in terms of f, and you're going to get homomorphism Okay, I'll stop here. I think I gave you a bit too much hint already. So the detail is left to the students. My suggestion is to use this and prove this is an isomorphism, one-to and onto and homomorphic. So that completes the definition of this factor group and all. And does it have anything to do with the coset structure? The answer is yes, of course, because this is the definition, right? But this preimage of function value, that's the same as coset. And of course, you can use right coset too, but they're the same. And as for this group operation, well, y1 and y2 are phi of x1 and phi of x2 respectively. So phi of x1 times phi of x2. And if I give you one more hint, because phi is homomorphic, you're going to get something like this by putting these together. So we can express everything in terms of coset expression. And this algebraic operation, this way or either that way, whatever you may want to call, you can re-express those in terms of cosets. Look at the first line. This one here, blue, is same as this blue. Yes, y1 is phi of x1, and this one here, green, is same as this green. y2 is phi of x2, and the preimage of the function value, that's a coset, and that's blue coset, x1k, and green coset, x2k. Yes, I can do that with right coset too, because left coset and right coset are the same. Now let's take the other viewpoint, right-hand side. What is preimage of y1 and y2? Well, this y1 is phi of x1, and this y2 is phi of x2, and then this is homomorphism, so I can put those together. And what do I end up with? Preimage of the function value, so we get x1, x2k. This operation, purple times brown, k. So what do you get? Coset operation. I don't like purple and brown anymore. Let's stick to blue and green. Why did I change? Let's stick to blue is 1, green is 2. Here you go. Blue, green. You see, the coset operation became x1, x2, k. So first line and second line are the same as we define like this. And is it well defined? Yes, it is, because y is coming from phi of g and they are unique. You don't really have to consider two different expressions of the same thing if you approach this way through homomorphisms. So everything is well defined, and we have the group structure, which we call the factor group, and then we can use the coset operation. Okay, that completes one approach of factor groups using cosets, using homomorphisms and kernels. The problem is, what if your subgroup is other normal subgroup not associated directly to a kernel? Well, you'll have to do a little bit harder way, and that's something we are going to do in the next video.